Here is a machine that turns one number into infinitely many. Pick an odd number, call it the seed. Now double it, and add 1. Double the original again to get 4 times it, and add 1. Then 8 times it plus 1. Then 16 times it plus 1, and keep going. Each step doubles the multiplier, and tacks a 1 on the end. One odd seed at the top, an endless column of outputs beneath it. Now ask the machine a single question. Somewhere in that infinite column, is there a prime? Try the seed 3. 3 doubled plus 1 is 7, and 7 is prime, first row, done. Try 5. 5 doubled plus 1 is 11, prime again. Try 7. Its first output is 29, prime. 13 gives 53. 15 gives 31. Every one of these lands on a prime on the very first step. For a few seeds you have to wait. 19 needs 6 doublings before it reaches 1217, which is prime. 31 holds out until the 8th row, landing on 7937. But the prime always shows up eventually. Every odd seed anyone had ever tested, sooner or later, produced 1. So you form the natural belief. Feed this machine any odd seed, wait long enough, and a prime is guaranteed to appear somewhere down the column. That belief is wrong. And the seed that breaks it is not gigantic, not strange. It is an ordinary looking number smaller than 100,000. The number is 78,557. It is odd. It looks like nothing special. It factors into just 17 times 4,621, 2 ordinary primes. Drop it into the machine and the column does something no seed is supposed to do. It never once hits a prime. 78,557, doubled, plus 1, composite, times 4 plus 1, composite, times 8, times 16, times 32, composite, composite, composite. We ran the first 5,000 rows by computer, and every last one factors. The column is infinitely long and, as far as any machine can reach, completely barren of primes. And this is not a story about looking hard and giving up. The emptiness is not a guess from a long search. It is a theorem. There is a clean, finite argument that 78,557 times 2 to the power n plus 1 is composite for every single exponent n all the way out to infinity. The argument is short enough to hold in your head. An odd seed whose entire infinite column contains no primes at all has a name. It is a Sierpinski number, after the Polish mathematician Wacław Sierpinski, who studied them in the 1960s. The whole job now is to see how a small number manages it. How can you possibly guarantee with certainty that not one term out of infinitely many ever comes out prime? The secret is a team of small primes working together, just 7 of them. 3, 5, 7, 13, 19, 37, and 73. The idea is to hand each prime a beat to patrol, so that no matter which row of the column you point at least one prime on the team divides that output and ruins it. Nothing gets through clean. Begin with the smallest, 3. Look at the even rows, exponent 2, 4, 6, and so on down. Run the arithmetic, and every single one of those outputs is divisible by 3, without exception. That is half of the entire infinite column, the even exponents, struck out by 3 alone in one move. A single small prime already does half the work. Now the others take their beats. Among the rows 3 does not touch. 5 claims a clean, regular family and divides every one of them. 7 covers another family, 13 another, then 19, 37, and 73 each take what is left. Every prime is assigned a fixed set of exponents and divides every output sitting on those exponents. The one thing that has to be true for the whole scheme to hold is this: between the 7 of them, every exponent from 1 upward is on somebody's beat. No row left unpatrolled, no gaps anywhere. But to even state that promise precisely, we need to know how these patrols repeat. And it turns out they repeat on a clock. Why should a single prime divide a tidy, regular set of exponents instead of a random scatter? Because powers of 2, looked at through a fixed prime, run in a repeating cycle. Take 3 again. The remainders of 2, 4, 8, 16 after you divide by 3 go 2, 1, 2, 1, and repeat forever with period 2. Through the eyes of 3, doubling is a clock with just 2 hours on its face. For 5, the cycle has length 4. For 7, length 3. For 13, 12. For 19, 18. For 37, 36. For 73, 9. Each prime carries its own little clock. Whether a prime divides a given output depends only on where the exponent lands on that prime's clock, nothing else. So the whole 7-clock system repeats the moment you go far enough for all 7 to return to their starting hour at once. That common period is the least common multiple of the cycle lengths of 2, 4, 3, 12, 18, 36, and 9. Work the least common multiple out, and it comes to 36. So the entire infinite behavior of the machine collapses onto a clock with 36 hours. Whatever pattern of divisibility happens for exponents 1 through 36 happens identically for 37 through 72, and again for the next 36, and forever after. To prove the machine never makes a prime, you no longer face infinitely many exponents. You face exactly 36 of them. Check those 36, and you have silently checked all of them at once. So here is the picture that makes it real. Lay out the 36 hours of the clock as a grid, one cell for every exponent from 0 to 35. The promise was that every cell is divisible by some prime on the team. So let us color each cell with the prime that does the killing, and see whether any cell is left blank. Reading the grid is just reading the clocks. A cell's hour tells you for each prime where that exponent sits on its cycle, and that alone decides whether the prime divides. So filling the grid is mechanical. Walk the 7 clocks, mark every hour each prime owns, and watch the cells light up. Watch 3 go first. It takes every even hour, 18 of the 36 cells, exactly half the grid, all painted for 3. Then 5 steps in and grabs 9 more cells in a clean every 4th hour rhythm. 7 takes 3 cells, 13 takes 3 more, and then the stragglers, 19, 37, and 73 each reach in and claim exactly 1 stubborn cell that none of the bigger patrols covered. Notice how lopsided the work is. 3 carries half the grid by itself, and 5 carries a quarter. Together, those 2 cheapest primes already cover 27 of the 36 hours, 3/4 of everything. The 4 larger primes exist only to patch the last 9 cells the small ones miss, and the 3 biggest each guard a single lonely hour. The team is mostly 1 prime doing the heavy lifting, with specialists plugging the leaks. Now add it up. 18, plus 9, plus 3, plus 3, plus 1, plus 1, plus 1. That total is 36. The grid is completely full, not a single hour is left uncovered. Not 1 exponent slips past all 7 primes. Every cell has an owner, and the instant the grid is full, the proof is over. Because a grid that repeats every 36 hours, and is full across 1 full turn, is full at every hour that will ever come. It is worth being careful about why a covered cell is genuinely dead, and not merely bruised. When we say 3 divides the output at the even exponents, 3 is not the whole number. It is a true factor sitting strictly inside a vastly larger one. That distinction is the whole game. Take the very first output at exponent 1. The patrol there belongs to 5, and 5 does divide it cleanly, but the output is enormous, and 5 is tiny. So that number equals 5 times a cofactor far bigger than 1. It is a genuine product of 2 smaller pieces, which is exactly what the word composite means. The same is true in every cell. The covering prime is always microscopic next to the output it splits, so it is always a proper factor, never the output itself. Nothing here is ever prime by accident of equaling its own divisor. We confirmed this directly by computer for the first 2,000 exponents. In every case, the assigned prime really divides, and really is the smaller piece, but the computer was only a courtesy. The clock argument already nails it down forever. Pick any exponent at all, however astronomically large. Reduce it modulo 36 to find its hour on the clock. Read off the prime that owns that hour. That prime divides the output and is dwarfed by it. So the output is composite, every time, with no exceptions, all the way out to infinity. That is what a covering set buys you, a claim about an endless list, settled for good by inspecting a grid of 36. Now the harder question, the one that turned this into a hunt lasting decades. We have shown 78,557 is a Sierpinski number. But is it the smallest one? The American mathematician John Selfridge found this number, and its covering set of 7 primes back in 1962. Finding one such number, though, does not prove it is the least. To claim that, you have to march through every odd number below it, all 39,000 of them, and show each one is innocent. Innocent meaning the machine, fed that seed, does eventually spit out a prime somewhere down its column. For the overwhelming majority that is easy, feed the seed in, and a prime appears within a handful of doublings, the way 3 and 5 did at the very start. Most odd seeds clear in the first few rows. The average suspect surrenders a prime almost immediately. The trouble is the rare seed that stays silent for a brutally long time. You double, and the outputs stay stubbornly composite, and you simply cannot tell whether a prime is waiting one row ahead, or whether you have stumbled onto a second Sierpinski number with a covering set you have not spotted. There is no way to know in advance how far you must look. The difference between a seed that breaks at row 50 and a true Sierpinski number that never breaks is invisible until you find the prime. By the year 2002, after decades of chipping away, the entire problem had been ground down to just 17 suspicious seeds. 17 odd numbers below 78,557, for which nobody had yet managed to find a prime. So a project formed, with a blunt name, 17 or Bust, aimed squarely at those 17 seeds. The strategy was simple to state. Take each suspect and keep doubling, searching for a single prime that would clear its name and prove it is not a Sierpinski number. The catch is that those primes can hide absurdly far out along the column. One seed was finally cleared by a prime whose exponent ran past 31 million, an output with more than 9 million digits, found only because thousands of volunteers pooled their home computers into one enormous search. To put that in proportion, the primes that clear these last seeds are larger than almost every prime humanity had ever written down before the project began. The suspects survived precisely because their primes sit so far out that no ordinary search would ever reach them. Seed by seed, against those odds, the list shrank anyway. 17 fell to 12, then to 9, then to 6. In 2016, the effort, by then absorbed into the larger distributed project called PrimeGrid, knocked out yet another, and the count dropped to a small handful. And there the matter still rests today. A handful of odd seeds below 78,557 remain unresolved. No prime found for them yet, but no covering set either, so no proof that they are Sierpinski numbers. The search is ongoing. Until that last handful is settled one way or the other, the careful sentence has to stand. 78,557 is the smallest known Sierpinski number, almost surely the smallest one that exists, and still, strictly speaking, not yet proven to be. So step back and take in the whole shape of it. A trivial-looking machine, an odd seed, doubled again and again, with a 1 tacked onto each row. For very nearly every seed, it eventually coughs up a prime, and you would bet your life they all must. But 78,557 sits inside a perfect trap. 7 small primes, 3, 5, 7, 13, 19, 37, and 73, split the labor of an infinite list among themselves on a clock with 36 hours, and between them they leave not 1 hour uncovered. Every output in the column, forever, has a small factor lying in wait. Not by luck, not by exhaustion of patience, but by design. A fact provable on a grid you can draw on a single page. That is the quiet power of a covering set. It takes a statement about infinitely many numbers, that none of them is ever prime, and pins it down with 7 primes and a check you can finish in an afternoon. The settled part is airtight. 78,557 works, beyond any doubt. The open part is whether anything smaller hides the very same trick, and that question has held out for more than 60 years. The machine looked like it could do nothing but manufacture primes. One unremarkable number proved it could be silenced forever, and we are still, to this day, making sure that nothing smaller can pull off the same disappearing act.